This lecture we are going to talk about enzyme inhibition kinetics. I think we already covered fairly on this topic. I think last two lectures I talked about the different type of enzyme inhibitors, and I also gave some expressions that may look like mechanism and kinetics, which allows you to identify what type of inhibitors that we are dealing with. So what we are going to do in this lecture is, let's say we have a competitive inhibitor, and if we need to calculate the rate of the reaction, and we need an expression for that. So that's what we are going to do. So it's the derivation looks almost similar to mechanism and kinetics, but some of the kinetic constant, you will see it has some additional parameter which is related to the inhibitor, which actually inhibits the enzymatic reaction. So by this time you should all know how a competitive inhibitor works. So I made some few diagrams which may help you to understand. So just to follow the what color pen I am having at the moment. Just follow this pink color line. So that will be our enzyme complex. You have enzyme, and then you also have a substrate. Just follow the pink pen wherever, or the line wherever I am drawing at the moment on the screen. And then we also have an inhibitor. So if you look at the structure, you have an enzyme, and then you have some binding pocket here, almost like a triangle shape, something like this. Just follow the pen wherever I draw. And then you have a substrate, so that can bind, that has a molecular structure which can exactly fit into this pocket of the enzyme, or we can call the binding site on the enzyme. And then we also have an inhibitor which have a similar molecular structure, something similar to substrate. And this part of your inhibitor, just follow the pink color pen. So this part of your inhibitor, they can fit into the binding packet of your enzyme. So eventually they can, so if your substrate go and attach to your enzyme, you will get an enzyme substrate complex, which is here. Alternatively, your inhibitor can target the same binding site on the enzyme, and if that happens, you will eventually end up with an enzyme inhibitor complex, which is shown here. Just follow the pen, wherever I write, that's the area you should focus on the screen. So that's the, so why we call it as a competitive inhibitor. So if you look at the molecular structure, you have some binding packet on the enzyme, and you have some site on the substrate and some site on the inhibitor. They can exactly come and fit into the same come and fit into the binding packet on the enzyme. So what it means is, like, both substrate and inhibitor competes for the same site on the enzyme. So that's why we call this type of inhibitors as competitive inhibitors. And once this inhibitor attacks your enzyme, and then it makes an enzyme inhibitor complex, obviously it's going to decrease the rate of your enzymatic reaction. So how the rate expression will look like, that's what you are going to derive. And if you don't have an inhibitor, you know how to deal with this a normal enzymatic reaction. We already solved the mechanism and kinetics following a set of assumptions, like you have an enzyme, you have a substrate, they make an enzyme substrate complex, and obviously they are a reversible reaction, and the concentration of enzyme substrate complex, they dictate the rate of the reaction. And then your enzyme substrate complex will eventually will be catalyzed by the enzyme. So and then you will get enzyme plus product. So normally the second reaction, enzyme substrate complex to enzyme plus product, that's a very slow reaction, and that's the rate limiting step, and that decides the rate of the reaction. So whatever I said, those are the assumptions behind the mechanism and kinetics, and we already derived that in the previous lectures. So we are going to do exactly something similar, but we are going to add one more parameter called as inhibitor. Obviously we have an inhibitor, so we have to include the concentration of your inhibitor into the rate expressions, and obviously we need some set of assumptions behind before we start to derive some rate expression for this type of problem. Then there are something that you should remember. So if just by looking at the diagram you can make this type of statements. So competitive inhibition typically occurs when the structure of your inhibitor resembles the molecular structure of the substrate. So this is a must condition. So only then they can compete for the same type of binding packets or the binding sites on the enzyme. So this is something that you have to remember. And then if you have a structurally similar materials, which means your inhibitor and also your substrate, if they are structurally similar, they can easily compete for the same site. So that's the main or a must condition. Or if I say, like, I have an enzyme and I have a substrate and I have an inhibitor that may look like a substrate, what type of inhibitor that we are dealing with, then you should know what to answer here. So this may be something like an objective type question that you can expect in the exam. And then here I have some few more rules that you can write based on this simple diagram. So what you have here, just follow the pink pen. Maybe change the color to blue, it will be easy to follow on the screen. So just follow the pen. So that's your enzyme complex, that's your inhibitor complex, and they come together, or they associate together to form an enzyme inhibitor complex. So in the mechanism and kinetics, we all know enzyme plus substrate, they come together to form enzyme substrate complex. In this case, since you have a structurally similar impurity, like structurally similar to that of your substrate, it can also form an enzyme inhibitor complex. And again, this is a purely physical process, very fast, and then it's a completely reversible process. So which means this compound can dissociate, your enzyme inhibitor complex can dissociate back into enzyme, leaving your inhibitor back into the solution. So that's the whole idea. So this is one more rule. So enzyme inhibitor complex needs to okay, forgot this rule. So this is something that you can expect. If you have an enzyme and inhibitor, same structure, they can form an enzyme inhibitor complex. And if you come back to the reaction, so if your reaction needs to proceed, you need an enzyme substrate complex. If you remember the mechanism and kinetics, we have enzyme plus substrate forms enzyme substrate complex. So this first process is completely reversible, it's purely a physical process and it's a very fast process. And then the second process is the main chemical reaction is happening, or the enzymatic reaction is happening. So this is a slow process where you have a lot of bond formation, bond breakage, and then you get a new molecule or a new product. So obviously for the reaction to proceed, you need enzyme substrate complex. The same rule applies here when we have an inhibitor. So still we need to form an enzyme substrate complex, even though if you have an inhibitor, in order so that this will dissociate into, or it will eventually get converted into enzyme plus product. So whenever we talk about the chemical reaction part, it's better we avoid using the word dissociation. Dissociation is a physical process. So let's say there is a chemical reaction which converts your enzyme substrate complex to enzyme plus product. So what we need in this type of reaction, when you're going to deal with an inhibitor, still we need this enzyme substrate complex. And if you look at this particular box, if you have an enzyme substrate complex, if you want the reaction to proceed in the forward direction, or if you want your substrate if you want to convert your substrate to products, obviously we need to make an enzyme substrate complex. So for that to happen, obviously this should dissociate back. So it should dissociate back to enzyme plus inhibitor. And now once you have a free enzyme, then your substrate can combine with this enzyme, and then eventually it can form an enzyme substrate complex, and this can be converted into enzyme plus products. So that's the whole idea behind that. So whenever we are going to deal with a competitive inhibitor, just there is one more rule that you have to remember. This enzyme inhibitor complex needs to dissociate, leaving the active enzyme for the substrate. So this is something that should happen during the course of your enzymatic reaction. So your inhibitor must first dissociate before the true substrate may enter the enzyme. So that's something you have to remember. And another thing that we have to take a note, or we can say it like a rule or maybe just a condition that happens in this type of reaction. So whatever you have here, just follow the blue pen. This is something we call it as enzyme inhibitor complex. Yeah. So whatever you have here, enzyme inhibitor complex, this is a completely dead end complex. So why do I mean by dead end? If you look at the structure, just look at the structure. So once your enzyme and inhibitor, they come together, and if they become enzyme inhibitor complex, you don't have that binding packet in this type of complex, which means your substrate, which is here, it cannot attach to this enzyme substrate complex, so you eventually get nothing. Or your inhibitor itself, which has whose molecular structure is almost similar to substrate, still it cannot bind to this type of enzyme inhibitor complex. So you will not have enzyme inhibitor complex either. So this is purely a dead end complex. It will exist in the solution, but obviously it will not make a big difference to the okay. So it will not make big difference to the product conversion rate. Yeah. Obviously it's going to affect the rate of reaction, but it will not convert anything. So if you have a dead end complex, which means your substrate concentration is going to be substrate concentration will remain constant. Yeah? So just imagine you have a reactor, you have a substrate concentration of 100 grams per liter. If you just have this enzyme inhibitor complex, if you plot your time versus substrate concentration, your substrate concentration will be constant, and that's because your enzymes inhibitor complex will never associate with your substrate, and that's the main reason you will have a constant substrate concentration in the reactor. So that's the meaning of the dead end complex. So it won't do anything to your substrate. And if the reaction needs to proceed, then obviously this enzyme inhibitor complex, it should dissociate into leaving your free enzyme that can associate or integrate with your substrate, forming an enzyme substrate complex. Okay. So, and then if it dissociates, obviously you will get your free inhibitor molecule in your solution. So that's the whole idea. I think now you know how the enzyme competitive inhibitor works. So whatever we learned so far, we used some nice diagrams. So we are going to now write a chemical reaction for this type of process. So before that, as I always use, we are going to give some notations. So I always like to use some common notation. So E for enzyme, I for inhibitor, and ES is enzyme substrate complex, and EI is enzyme inhibitor complex. So these are the notations that we are going to use. So let's do that. So sometimes for convenience, for concentration of enzyme, I put a bracket. So it means concentration of enzyme. So if I write something like this, this is concentration of inhibitor. Within square bracket, if I write ES, which means concentration of enzyme substrate complex. But when I'm going to derive, sometime I may or may not use the square bracket. So pay attention what I talk while you are watching this video. Yeah. So let's write the enzymatic reaction. As I said, we have enzyme, we have substrate, we have inhibitor in the reaction. So if your enzyme and your inhibitor, if your inhibitor and your enzyme, if they associate together, they will eventually end up, or they will form enzyme inhibitor complex. Okay, and again this is a reversible reaction. This is purely a physical process, nothing big is happening. So this is enzyme inhibitor complex. And then if your enzyme and your substrate, if they associate together, then you will end up with an enzyme substrate complex. Again, this is completely reversible. This is completely reversible reaction. And then let's say your enzyme substrate complex, so they dictate the rate of your reaction. So enzyme substrate complex eventually end up with your enzyme plus products. So your substrate in the enzyme substrate complex will be converted into enzyme and your product. So you get your enzyme back for your to convert your next molecule into product, or this enzyme may even associate with the inhibitor, and then it can again form enzyme inhibitor complex. So let's give some kinetic constants. Let's say Kf1, that corresponds to the forward reaction for first process, enzyme plus substrate, that they associate to form enzyme inhibitor complex. And then we can give some Kr1, something for the reversible reaction, enzyme substrate complex dissociate into enzyme plus substrate. And then for the same here, let's say, or maybe just let's give an equilibrium constant. Let's call it as Ki. So enzyme plus inhibitor, they associate to form enzyme inhibitor complex, again completely reversible process. And enzyme substrate complex, here is where the main reaction is happening. So your substrate will be converted into enzyme plus product. Let's say Kf1, so that's the forward reaction. And please note that in many textbooks they claim that this is a reversible reaction. I'm going to just assume this is a irreversible, which makes sense to me. Anyway, this doesn't make so let's assume that this is a irreversible reaction, and then let's do the calculation. Yeah. So this part is exactly the chemical reaction which is happening in the Michaelis-Menten expression when we are happening in the so this part of the reaction, it will resemble the same reaction which happens during a pure enzymatic reaction. So you all know how we derive the Michaelis-Menten type expression. So there we have this second reaction where your enzyme substrate complex will move forward, and then you will end up with enzyme plus product, and this is an irreversible reaction, and you have a kinetic constant. Let's put Kf2. Yeah. Or we can even just call it again as K catalyst. Why not? So let's derive. So okay, before deriving, pay attention. So here you have two physical process. So association of enzyme plus substrate to enzyme substrate, and then association of enzyme plus inhibitor to form enzyme inhibitor complex. And enzyme inhibitor complex, this is a dead end complex. So dead end complex means this EI will never associate with substrate. This will never happen. Or EI will never associate with another inhibitor, so this will never happen. So that's why this is called a dead end complex. So let's derive the expression. So let's focus on this enzyme plus inhibitor that gives associate to form enzyme inhibitor complex. So we know we have an equilibrium constant. So let's write. So your equilibrium constant Ki will be equal to concentration of your enzyme, concentration of your inhibitor, divided by concentration of your enzyme inhibitor complex. I hope you all know this general rule in chemistry. If you have, I don't know, A plus B going to C, if it's an irreversible reaction, you have a kinetic equilibrium constant. That equilibrium concentration will be equal to concentration of A, concentration of B, which is on the reactant side, divided by whatever the concentration that you have, concentration of the molecule that you have on the product side, which is C. So that's the same rule that we are applying here. So let's call this as equation 1. So we have the equilibrium constant for the inhibition reaction. Ki is equal to your reactant side divided by your product side. So let's give an equation number for that. And then let's say, okay, another thing that you should remember. So once you start your reaction, you will have enzyme. Obviously, these are like freestanding enzymes which can either associate with your inhibitor or associate with your enzyme substrate complex. And then once you add that, once you start your reaction, you will have some enzyme substrate complex, and then you will also have some enzyme inhibitor complex inside the reactor. So in this case, your total enzyme concentration at any instant of time, so total enzyme concentration, so you may expect this type of questions in not question, like I may ask you to derive an expression that allows you to calculate the rate kinetics, or the not rate kinetics, maybe derive a rate expression for a competitive inhibitor, something like that. So you should know how to derive the expression, and you also should write about some of the basic assumptions that you need to derive this type of expression. Yeah? So you have what I was talking about. Yeah, total enzyme concentration at any instant of time, that will be equal to enzyme concentration. This is your freestanding enzymes, enzyme substrate, plus your enzyme inhibitor complex. So concentration of all these three, that will be nothing but equal to your total enzyme concentration in the reactor at any instant of time. So let's give some number for this equation. Let's call equation 2. And then what else? And always remember that we cannot measure the concentration of enzyme substrate complex and the enzyme inhibitor complex. So we should always find a way to eliminate these two parameters in the rate expression. So from equation 1, we have which is here, Ki is equal to concentration of E multiplied by concentration of I divided by concentration of enzyme substrate complex. So from equation 1, we can get the concentration of enzyme inhibitor complex, so which is equal to concentration of your enzyme, concentration of your inhibitor divided by your equilibrium constant, which is Ki. Okay, which is not bad. So let's call this as equation 3. So substitute equation 3 in equation 2. So that will be equal to E total. So we have to replace EI in equation 2 with equation 3. So E total will be equal to concentration of enzyme plus concentration of enzyme substrate complex, plus instead of concentration of enzymes inhibitor complex, we are going to replace it with equation 3, which is nothing but concentration of E multiplied by concentration of I divided by your equilibrium constant, one of the equilibrium constant, Ki. So this is okay so far. So you can write this equation into, let's rewrite this expression. E total is equal to concentration of enzyme plus concentration of enzyme plus multiplied by inhibitor divided by Ki plus concentration of enzyme substrate complex. So what I'm going to do is I'm going to take E, the common factor outside, so that will be equal to, you'll get some expression like this, 1 plus concentration of inhibitor divided by your equilibrium constant Ki plus concentration of the enzyme substrate complex, E total. Yeah. So let's give a number for this expression. Let's call it let's call this equation 4. Let's check what we have here. Km multiplied by this is so far good. Just checking what I'm doing now. I think this part is okay to me. E equal to E total, and then so let's E total we have here, and then what else we need to do? Let's focus on the other side of the reaction, which is here. You have, go back to this page, like you have an enzyme plus substrate, which gives rise to enzyme substrate complex. So we can write an equilibrium constant for that. So if you remember the derivation of Michaelis-Menten expression, so we know if we have enzyme plus substrate, enzyme substrate complex, let's assume the equilibrium constant is Km. In this case, Km will be equal to, again same, enzyme multiplied by your substrate concentration divided by your enzyme substrate concentration. I think this is good so far. So let's call this as equation 5. E total equal to, I think to me it looks fine. Okay, and now so okay, we have to write, we don't know what's the concentration of the enzyme substrate complex, so let's try to eliminate that one. So that will be enzyme substrate complex, that will be equal to concentration of your enzyme multiplied by concentration of your substrate divided by Km. Yeah, so I'm not using any book at the moment, I'm just deriving it by myself. But I read this in some book, but I tried to solve it one time. So enzyme substrate complex, you get concentration of enzyme multiplied by concentration of substrate divided by Km. And then what we have here, we have enzyme concentration somewhere around here. Okay, let's call this as equation 6. So if we go back to equation 4, what we have here, if we go back to equation 4 here, let's try to get the value of enzyme, concentration of enzyme from equation 4. So from equation 4, I know I'm taking extra bit of time, but I don't want to do any mistake while deriving this expression. So we can rewrite the equation 4 like this. So your enzyme concentration multiplied by 1 plus inhibitor divided by Ki, that will be equal to E total minus ES. So I'm going, just for convenience, I'm going to call this parameter as alpha. So alpha will be equal to 1 plus concentration of inhibitor divided by equilibrium constant, or you can call, okay, just you can call inhibition constant or equilibrium constant Ki. So let's call this as equation 7. So what it will become, so your concentration of E multiplied by alpha, that will be equal to total concentration of your enzyme minus enzyme's concentration of your enzyme substrate complex. So your concentration of enzyme will be equal to E total minus enzyme substrate complex divided by alpha. I think this is something we need. So let's call this as equation 8. So if we go back to equation 5 maybe. Okay, I think we have to use equation. So substitute value of enzyme concentration in equation 8 in equation 5. So we know the concentration of E from equation 8. All we need to do is we substitute this equation 8, which is shown here, in equation 5. So equation 5, I'm going to rewrite it. Enzyme concentration multiplied by substrate concentration divided by enzyme substrate concentration. So we need to substitute this value for your enzyme. So I'm going to do that. So Km will be equal to E total minus enzyme substrate complex, let's put a square bracket, divided by alpha, okay, minus enzyme substrate complex, concentration of enzyme substrate complex, the whole value divided by again enzyme substrate complex. So this is, we are just rewriting the equation 5, and then we replaced enzyme concentration in equation 5 with this whole value here, which you see. So what I'm going to do is I'm going to expand this full expression. So so Km is equal to, let's try to, so what I'm going to do is I'm going to expand this expression so that we can calculate the enzyme substrate complex. So this is something that we cannot measure, so that's why we have to calculate it theoretically. So let's do that. So Km multiplied by enzyme substrate complex, that will be equal to E total minus enzyme substrate complex. No, E total minus, I think we did some mistake somewhere. E is equal to E total minus ES, that's correct. Km is equal to E multiplied by S. Okay, this should be multiplied, and this is not enzyme substrate complex, this is a substrate complex. If we go back to equation 5 here, so you have a substrate complex here, that's a multiplication symbol, so this is just multiplied by, so Km will be equal to, or Km multiplied by ES, that will be equal to E total minus ES, the whole multiplied by your substrate concentration. Yeah, so let's just expand that expression. It's a bit of calculation, but it's not tough to do. Substrate concentration minus E total multiplied by your enzyme substrate concentration. So bring this value to the left hand side of the expression. So Km multiplied by enzyme substrate concentration plus E total multiplied by enzyme substrate concentration, that should be equal to where this alpha value, okay, alpha and alpha plus E total multiplied by is equal to E total. No, I think we are doing really some big mistake, so let's cut this part. So you may do the same mistake like me. Km, that will be equal to E total multiplied by your substrate concentration minus enzyme substrate concentration multiplied by your substrate concentration. Yeah, now it makes sense. So Km, enzyme substrate concentration, sorry, we also have an alpha value here, equal to E total minus your multiplied by your substrate concentration. So we take the enzyme substrate complex multiplied by substrate, this one to the left hand side of the expression, so plus enzyme substrate concentration multiplied by your substrate concentration. So finally we get something like here, enzyme substrate complex multiplied by alpha plus enzyme substrate complex multiplied by your substrate complex, that's equal to E total into substrate concentration. Yeah, so that's what we have at the moment. So let's take enzyme substrate complex, the common factor outside. So enzyme substrate complex, take it out, Km multiplied by alpha plus your substrate concentration, that's equal to E total multiplied by your substrate concentration. Okay, so which means your enzyme substrate complex, that's equal to, this is something that we cannot measure but we can calculate theoretically, E total substrate concentration divided by Km alpha plus your substrate concentration. Okay, so let's go back to the main chemical reaction which we are deriving or which we are dealing with now. So if you look into this main expression, maybe let me change the color. If you look into this main expression which is here, so this is your actual chemical reaction. Yeah, so this is the actual catalytic reaction where your enzyme substrate complex are eventually get converted into enzyme plus product, which is a new molecule. Obviously this is going to be the slowest reaction. So again, like what we did in when we are deriving the Michaelis-Menten expression, so the rate of this reaction is dictated by the slowest reaction, which is this expression, enzyme plus substrate, that gives enzyme plus products. So let's call it as K catalyst again, something similar to our Michaelis-Menten expression. So for this part of your equation or your reaction, say like enzyme substrate complex gives your enzyme plus products. So let's call it as K catalyst again for convenience. You can use any notation, who is going to stop. So K catalyst, and then for this since this is the slowest reaction and decides the overall rate of reaction, so let's call the rate of the reaction is equal to K catalyst multiplied by your enzyme substrate complex. So what this expression says, or this law states, the rate of your reaction is just simply proportional to the kinetic constant of this forward reaction, let's say K catalyst, and it depends only on the concentration of the enzyme substrate complex, not on the concentration of enzyme or not the concentration of enzyme inhibitors. Yeah. So the rate of product formation depends on the concentration of the enzyme substrate complex. So this is something you have to remember. Yeah. So this is exactly the same assumptions that we made when we derived the Michaelis-Menten expression. So let's call this what, I don't know, we have equation 8. Okay, let's call this enzyme substrate complex equation 9, and let's call this rate expression as equation 10. So we know what's our enzyme substrate complex concentration is. So that we can get from equation 9. So substitute equation 9. So we know what's our enzyme substrate complex concentration. So substitute here in equation 10. So we get the rate of reaction that will be equal to K catalyst multiplied by E total multiplied by your substrate concentration divided by Km alpha plus again your substrate concentration. Yeah. So that's the rate of the reaction when we are going to deal with a competitive inhibitor. So let me write this in the next page. So competitive inhibition, and the rate expression is given by R is equal to K catalyst E total concentration of your enzyme multiplied by your substrate concentration divided by Km alpha plus your substrate concentration. So, and if you write the Michaelis-Menten expression, which is obviously which does not involve any inhibitor, so which is a pure enzymatic reaction, we know the rate expression is given by K catalyst E total multiplied by substrate concentration Km plus your substrate concentration. So I'm going to give some number for this expression. Let's give equation 10, and this is your Michaelis-Menten expression. So if you compare equation 10 and 11, you see here you have an alpha parameter in equation 10. So whenever we are going to deal with a competitive inhibitor, you have some parameter which is associated with your inhibition constant together with your Km value. So which means just by looking at mathematical expression, one thing you can understand is so when we, let me write it. So when we deal with a competitive inhibitor or inhibition process, your inhibitor is going to affect or alter the inhibitor will alter the value or affect the kinetic constant Km in the monode expression, in the Michaelis-Menten expression. So if you want, we can rewrite equation 10 something like below. So R is equal to K catalyst multiplied by total concentration of enzyme multiplied by your substrate concentration divided by Km dash plus your substrate concentration. So this almost look identical to your Michaelis-Menten expression. The only difference is the kinetic the equilibrium constant Km, it involves an additional parameter. So Km dash is equal to Km multiplied by alpha, which is equal to Km. We know what the alpha value is from equation, what's that equation? Is equation 7. 1 plus inhibitor concentration divided by inhibitor constant or inhibition constant. Okay, Km. So if we really do an experiment, say like we have an enzyme and then we have a substrate, and then let's decide we are performing this reaction in the absence of inhibitor, so no inhibitor. And then if for this type of reaction, if you plot say like your substrate concentration versus your initial velocity here, so you will get something like this. So this is like a so no inhibitor. This is pure enzymatic reaction in the absence of any inhibitor. Yeah? Obviously your Michaelis-Menten expression will help you to calculate the kinetic constant, which is Km, and this is your mu max. So we all know this is our mu max, maximum initial velocity, and exactly half of that is around here. and whatever the substrate concentration, when your initial velocity is equal to half of your maximum initial velocity, so that should give your kinetic constant Km. Yeah, so this is according to the rule of the Michaelis-Menten kinetics. And now you imagine you perform the same experiment, enzyme plus substrate, and this time we add a competitive inhibitor. You will get something like this. Just maybe let me change the color. Follow the green color. So you will get something like that. And then something it meets mu max, something like this. So what this green color states, so if you look at this type of image, you see here you are when you look at the substrate concentration and your initial velocity, your initial velocity reaches mu max when your substrate concentration is higher, but when your substrate concentration is very low, your inhibitor is altering your initial velocity. Say like this is your substrate concentration, say 10 grams per liter, and say this is initial velocity of some number, let's put 1, and then in absence of inhibitor your initial velocity at that substrate concentration, say it will be 2, yeah, something like that. Yeah. So what it says is like and then another thing that you can notice is if you take mu max by 2, which is this line, I will change the color again. Let's follow the red color pen. So this is our mu max by 2 line, and then if we try to calculate the substrate concentration when your maximum when your initial velocity is exactly half of the maximum initial velocity, that's somewhere around here, which means your Km value is altered already. So what it says is like, so when we have competitive inhibitor, your inhibitor will alter only the Km value but not your maximum initial velocity. Yeah? So your Km value will be altered, your new Km value will be altered by some amount which will be multiplied by alpha. Yeah? So this is nothing but your Km dash. So whenever we have a competitive inhibitor, it will not alter your mu max, but it will alter your Km value. Yeah, so that's the main conclusion that we can make just by looking at the graph and also just by looking at the expression. If you look at into equation 10, clearly we see that you have a alpha value associated with this equilibrium constant Km. So which means it's going to alter only this Km value, and it will not affect your mu max. So that's something you have to take it in your mind. And another reason that this happens is if we go back to that expression, or maybe I can rewrite it again. So enzyme plus inhibitor plus substrate. So this is a reversible reaction. You get enzyme substrate complex, then you get enzyme inhibitor complex, and then here you get your enzyme plus product. So if you look here, the rate of the reaction, it depends not only based on your substrate concentration, it also depends on your inhibitor concentration, yeah? And also how strong the substrate will bind to your enzyme, how strong this inhibitor will bind to your enzyme. Yeah? So that dictates. So if your inhibitor strongly binds to the enzyme, then you will get a dead end complex, enzyme inhibitor complex, and obviously you will have less enzyme in the solution. So which means you will have less enzyme substrate complex, and obviously it's going to affect your rate of reaction. So how many molecules or how many number of enzyme substrate complex are getting converted into product. So this number will decrease if more and more inhibitor molecule attached to the enzyme molecule. Yeah, so that's the message. And another thing that you should remember is say like when your substrate concentration is low, say like you have one enzyme and then you have only one substrate, and then you have say like maybe 3 inhibitors. So it is more likely, or it is more probable, that you will end up with enzyme inhibitor constant, yeah, sorry, enzyme inhibitor complex. And obviously this is going to dissociate back, and then again at some instant of time your substrate may attach to this, your one substrate may attach to this free enzyme, and then again you will get enzyme substrate complex. But in this whole process, what's happening is somehow you are delaying the process. So you have an enzyme inhibitor complex that takes some time, and then it disintegrates into enzyme plus inhibitor, that takes some time, and then your substrate may go and attach with your enzyme. Then you may get the enzyme substrate complex, which should eventually get converted into products plus your enzyme. So something is getting delayed due to the action of your enzyme. But on the other hand, if you just imagine, if you have another case, let's write something like or maybe I will draw some picture. You have one enzyme, and then this time you have say like 3 substrate molecules, and you have only one inhibitor molecule. Then it is more likely that your substrate will attach to this enzyme. The probability is more high, and then it is more likely that you will eventually end up with enzyme substrate complex, which will proceed, or which will eventually converted into products plus your enzyme. So what it means, or what you can understand from this simple diagram is, if your concentration of your substrate is high, your inhibitor, the effect of your inhibitor on the rate of reaction will diminish eventually. Yeah? Just imagine you have only one inhibitor, and then you have say hundreds of your substrate. Then obviously it is more likely that your substrate will come and attach to your enzyme, and then more likely you will always have enzyme substrate complex, which mean your inhibitor will never ever dictate or reduce the rate of, or decrease the rate of your reaction. So that's why if you go back to this graph, what you see here is when your substrate concentration is increasing, and eventually when it's very very high, your mu max value, which is here, just follow the reading, is not affected due to the presence of inhibitor. So when your substrate concentration is high, your initial velocity will reach the mu max, and obviously it will not be influenced by your inhibitor. So this is another message that you should take home. So whenever we are going to deal with a competitive inhibitor, when your substrate concentration is very very high when you compare to the concentration of your inhibitor, obviously the effect of inhibitor on the overall rate of the reaction will be negligible. Yeah, so your initial velocity will be indifferent to that of the pure enzymatic reaction. Yeah, so that's something that you have to remember. So what we learned so far is the actual mechanism involved in the competitive inhibition kinetics, how it works, and what are the type of reactions that are the process that happens. Like you have 2 physical process and 1 chemical reaction, and the 2 of those physical processes are irreversible, and that 1 chemical reaction, let's assume it's irreversible, and then it goes only in the forward direction. And you have two equilibrium constant. One is Ki, another is Km, and then Ks is associated with your inhibition pathway, and then your Km, obviously that's related to enzyme plus substrate, which goes to enzyme substrate complex. And then you need to make a product, you need enzyme substrate complex in the reactor. That's another thing that you have to remember. And obviously the whole process is dictated by the catalytic reaction, which is the slowest reaction. So we have a kinetic constant kcat, that's the enzymatic kinetic constant. So sorry, kinetic constant of the enzymatic reaction, something you have to remember. And then obviously we derived mathematically the concentration of your enzyme inhibitor complex. We derived mathematically the concentration of enzyme substrate complex. And then we know whenever we have an inhibitor, competitive inhibitor, the total enzyme concentration at any instant of time will be just equal to all these values which you are seeing here, like enzyme concentration, enzyme substrate, and enzyme inhibitor complex. And from that finally we managed to derive a rate expression that looks like a Michaelis-Menten expression, but it's not exactly. You have one more value, Km multiplied by alpha. And then another thing that we learned is so whenever we deal with a competitive inhibitor, it's not going to alter your mu max, but it will alter your Km value. Yeah, so that's something you have to keep it in your mind. And we will solve some problem related to competitive inhibitor, and we also try to calculate this alpha value. We'll try to calculate the Ki value. So alpha is nothing but 1 plus concentration of inhibitor divided by Ki. So if you manage to calculate Ki, then if we know the concentration of inhibitor, then we can calculate alpha very easily. Yeah. I think this is good so far. So I will stop now, and then in the next lecture what we can derive is we will derive some expression for uncompetitive inhibition. So uncompetitive inhibition, this is even more easy. So for uncompetitive inhibition you have again some enzyme plus substrate will give enzyme substrate complex will goes to enzyme plus product. So uncompetitive inhibitor is like so we will have some inhibitor that will not compete for the site in the enzyme. So say like this is your enzyme, so this is your substrate molecule. Let's say we made an enzyme substrate complex, and we have an inhibitor with a funny shape, say like something. Let's say this is our inhibitor, so this one will go and fit in here. So what we'll do is like our inhibitor will only act on enzyme substrate, but it will not compete with substrate on the directly on the site on the enzyme. Yeah, so that's how uncompetitive inhibition will work. So it's slightly tricky. Maybe I have to draw a better picture. Maybe I will do that in the next lecture, but that's what we are going to do. So for competitive inhibitor, we have an inhibitor that competes with your substrate complex for the same binding packet in the enzyme. But uncompetitive inhibition is you have an inhibitor that will not compete with substrate. Yeah, so but they will have a completely different funny shape maybe, but your inhibitor, but that can exactly bind with the enzyme substrate complex. So probably your enzyme substrate complex may have some special binding packet, so where your inhibitor can go and accommodate. So instead of enzyme inhibitor complex, you will have enzyme substrate inhibitor complex, slightly a different type of complex. So for this we need to derive some expression, so that we will do it in the next lecture. So thanks for listening, and this is going to be slightly this may be a slightly tough topic, especially if you do not have a good background in chemistry. Like if you don't know what's an equilibrium constant is, then you may find it really difficult, but I'm 100% sure you know what's an equilibrium constant. And if you have some chemical reaction, say like A plus B goes to C, you should know how to get the equilibrium constant. Yeah? So I will stop now. Thanks for listening.